Hello everybody, this is Bert Dixon here presenting on section 8.2 on arithmetic series and sequences. So first we'll start with arithmetic sequences. So an arithmetic sequence is a sequence of numbers in which the consecutive terms is constant. And so that means if we start with a number like 2 and then we add the same number each time, let's say we add 3, we get 5, then we add 3 again, we get 8, and we add 3 again, we get 11, and so on. That would be an example of an arithmetic sequence. Okay, so in example 1, we are going to look at each of these sequences and decide whether or not they're arithmetic. And if they are arithmetic, then we want to state the common difference. We usually refer to the common difference of an arithmetic sequence as D. So in example A, the difference between 7 and 11 is 4, so we would add 4 to get from 7 to 11. And then to get from 11 to 15, we would add 4 again, and then add 4 again to get 19, and then add 4 again to get 23. So since the difference is the same for each of the consecutive terms, then we'd say it is arithmetic. And the common difference is equal to 4. So go ahead and take a look at examples B and C and decide on your own if these are arithmetic or geometric, if they're arithmetic or not. And if they are arithmetic, state what the common difference is. So go ahead and press pause on your video player, work those two examples out, and then press play when you're ready to see the solutions. So in example B, the difference between the first two terms is 3. So we would add 3 to 2 to get 5. But then to get from 5 to 9, we would have to add 4. And to get from 9 to 14, we would have to add 5, and so on. So the difference is not consistent. And so this is not arithmetic. There is not a common difference from one term to the next. So it's not arithmetic, and so there's no point in stating the common difference because there isn't a common difference. Okay, now let's take a look at example C. To get from 5 to 8, we would have to subtract 3. To get from 5 to negative 2, we'd have to subtract 3. To get from 2 to negative 1, we would subtract 3, and then subtract 3 again to get to negative 4. So this is arithmetic. The common difference is negative 3. So in our next example, we're going to see if we can write an algebraic rule that will determine any given term. So we call that the nth term. So if we wanted to know the 10th term or the 16th term, or in this case the 18th term, denoted a sub 18, it'd be nice to have a formula that would give us that. So let's see if we can figure out a pattern here so that we can come up with a formula. So this first term, we would call that A1. The second term we would call A2, A3, A4, and so on. And A1 is just a plain old 7. But A2 is 7 plus 3, which happens to be the common difference. And then 13 is 7 plus 2 3s. So that's 7 plus 6 gives us 13. And then 16 is 7 plus 3 3s. So 7 plus 9 is 16, and so on. So compare the subscript to the number of 3's that we're adding on. For the first term, we're not adding on any 3's. For the second term, when the subscript is 2, we have 1 3. When the subscript is 3, we have 2 3's. When the subscript is 4, we have 3 3's, and so on. And so we see that the number of 3's that we're adding on is 1 less than the subscript. This 3 is 1 less than 4. This 2 is 1 less than 3. 1, There's 1 3 here, that's 1 less than 2, and so on. And so in general, to get to the nth term, which we would call a sub n, we would do 7 plus n minus 1 times the common difference, which in this case is 3. So our rule for this first example, to get the nth term, we would just do 7 plus n minus 1 times 3. So for example, if we wanted the 10th term, we would just do 7 plus 10 minus 1 times 3, because n is 10, so we put 10 in place of this n and this n. And so that turns out to be 7 plus 9 times 3, or 34. So we were asked, in this example, we were asked to find the 18th term. So a sub 18, applying this formula, is 7 plus 18 minus 1 times our common difference 3. So that's 7 plus 17 times 3, or 58. So the 18th term of this sequence is 58. So we have created our formula. A sub n equals 7 plus n minus 1 times 3. And we have found the 18th term, which is 58. Now, I do want to also mention that this term generating formula that we created right here can also be simplified. If we distribute the 3, that's 7 plus 3n minus 3, which could also be written as 3n plus 4. So that would be another way that we could write our term generating formula, would be 3n plus 4. So notice that we get the same answers. If I wanted to know the 10th term, we got 34 last time. Let's try it using this new simplified formula. That is 3 times 10 plus 4, so 30 plus 4, of course, is 34. We get the same answer. The 18th term, 3 times 18 is 54, plus 4 is 58. Again, the same answer we got the last time. So you can express your the nth term rule either way. You can leave it in this form, or you can simplify it like this. So in general, before we get on to the next example here, in general, we should write down that for any arithmetic sequence, the nth term rule is going to be a sub n is equal to the first term plus n minus 1 times the common difference. So now we have a kind of a formula that we can use anytime we want the nth term formula for an arithmetic sequence. So let's try that on example B. So applying this formula, we'd have a sub n is equal to the first term, that's 15, plus n minus 1 times our common difference. So to get from 8 to 15, that's going down 7. To get from 8 to 1, to get from 15 to 8, we go down 7. To get from 8 to 1, we go down 7. To get from 1 to negative 6, we go down 7. So our common difference is negative 7. And so now we have our term generating formula. Again, we can leave it like that, or we can simplify it. If I simplify this by distributing the 7, or the negative 7, that would be negative 7n plus 22. And so we can try that. Let's say, since we know that third term is 1, let's try it out and see if it works. So a sub 3, the third term, should be negative 7 times 3 plus 22. Well, that's negative 21 plus 22, which is 1, and that matches what our sequence says for the third term. So it looks like our formula works. Now we still have the same directions that we did up above. We're supposed to be finding the 18th term. So now we have a formula that works. Let's go ahead and find the 18th term. By plugging in here, that would be negative 7 times 18 plus 22. So that is 56 and 70, negative 126 plus 22 is equal to negative 104. So a sub 18 is negative 104. Go ahead and try example C. So you can press pause on your video, try example C, and then when you're ready to see the answer, go ahead and press play. In this sequence, our first term is 7. Our common difference is 4. And so D equals 4. So now we're ready to write our nth term formula. A sub n would be the first term, 7, plus n minus 1 times our common difference. So that is a valid nth term rule, or we can simplify that, and that would be 4n plus 3. So either one, they both do the same thing. So again, we can test it out. This is the 5th term, 1, 2, 3, 4, 5. So this is a sub 5. So let's see if our formula gives us a sub 5 correctly. So a sub 5, according to this formula here, would be 4 times 5 plus 3. So that is 20 plus 3, or 23. So that seems to work. So now that we're confident that our formula works, we can find the 18th term. That's going to be 4 times 18 plus 3. And 4 times 18 is 72, plus 3 is 75. So a sub 18 is 75. Okay, so in the next example, we're given one of the terms in a sequence and the common difference, and we want to find the nth term rule. This time we have a little bit more work to do because we don't have the first term in order to use the formula that we used in the past. So then once we find the formula, then we'll list the first 4 terms. Okay, so we do know that in any arithmetic sequence, the nth term is the first term plus n minus 1 times the common difference. So let's fill in what we know. We know that a12, so when n equals 12, a sub n is 52, because that's what was given up here. And we don't know a1. We know n is 12, and we know the common difference is 6. So I was able to fill in everything into this formula except for a1 because I don't know a1. So that's our only unknown. Now we're able to solve for a1. I have 52 equals a1 plus 66. Subtract 66 from both sides. And I have a second, I'll create a little more space. So I subtract 66 from both sides. I have negative 14 equals a1. So now that I know what a1 is, I can write my formula. A sub n is equal to negative 14 plus n minus 1 times 6, which could also be written a sub n is equal to 6n minus 20. So now we can use that to generate the first 4 terms, or we could just simply write down our first term, which we found was negative 14, and then add 6 each time. So the next term should be negative 8, the next term should be negative 2, the next term should be 4. So those are the first four terms, A1, A2, A3, and A4. And that's it. We found everything the problem asked for. Write a rule. We did that there. And then list the first four terms. We did that there. Okay, so now you give it a try. Press pause on the video. Try example B. And then press play when you're ready to see the solution. Okay, so we'll go about this very much the same way we did the last one. We'll start with a sub n is equal to a1 plus n minus 1 times the common difference. That works for every arithmetic sequence. And we're given information about when n is 11, a sub n would be 50. N is 11, so we have 11 minus 1, and our common difference is 7. So now we have 50 equals a1 plus 70. Subtract 70 from both sides. a1 equals negative 20. And so now we can write our rule. Our rule is a sub n is equal to the first term plus n minus 1 times the common difference. That's fine to leave it like that, or you could simplify and write 7n minus 27. And then we can use that to generate the first four terms. Our first term is negative 20. And then we're going to add 7 each time. So negative 13, negative 6, and positive 1. Okay, so next we're now going to look at arithmetic series. So the difference between a sequence and a series is that in a sequence we just list the numbers like we did up here in this previous example. That's a sequence. A series is when we have a sequence of numbers that we add. And so, for example, we have a sequence 7, 11, 15, 19, 23, 27. If we put a plus sign in between instead of a comma, it becomes a series. So that means we're adding all of those terms. And so to find the sum of arithmetic series, I want you to recognize a pattern. If I add the first term and the last term, I get 34. If I add the next term, the second term, and the second to the last term, I also get 34. And then if I add the two middle terms, I also get 34. And that will work for any arithmetic sequence we look at. So what we want to recognize is that when we get longer and longer series, what we want to recognize is that the sum is always going to be, the sum of the first n terms is always going to be the first term plus the last term. So we would call that a1 plus an times the number of pairs that we would get. So that's the number of terms, which is n, divided by 2. So in this case, we see that the sum of the first, we have 1, 2, 3, 4, 5, 6 terms. The sum of the first 6 terms is the first term plus the last term times the number of terms, which is 6 over 2. And the significance of that is the first term plus the last term gives us 34. And then the number of pairs that we get when we pair these numbers up, we did first and last, and then we did second to the last and the second term and the third term and the third from the last. So every time we pair them up, we get 34. So how many pairs of 34 would we get? Well, it's just half the number of terms that we had. So if we have 6 terms, we're going to get 3 pairs. So 6 over 2 gives us 3. So that's 34 times 3 is 102. And so if you added those up individually or with a calculator, you would get the same answer of 102. But I just wanted you to recognize the pattern that the first term and the last term are always going to give you the same sum as if you did the second term and the second to the last term. and the third term, and the third to the last term, and so on in any arithmetic sequence that will happen. So now we have a formula that we can use to find the sum of the first n terms. So looking on at example 4, this series is written first in sigma notation. So if we expand it, at least some of the terms, we don't have to list all 10 of them. To write down this series, we're going to plug in 1 for I, and that gives us 9. Then we're going to plug in 2 for I, and that gives us 18. Then we're going to plug in 3 for I, and that gives us 9 times 3 is 27. And the fourth term, when I plug in 4 for I, would be 36, and so on, until we get to when we plug in 8, for example, we would have 72. When I plug in 9, I would have 81. And when I plug in 10, I would have 90. So I didn't list the whole sequence out, but I did list enough for you to recognize that we're going to see the same pattern. If I add the first term and the last term, I get 99. If I add 18 and 81, I get 99. This one and this one adds up to 99, and so on and so on. So how many 99s would we get? Well, from the sigma notation, we can tell that there are 10 terms. So if there are 10 terms, then I would get 5 pairs that all add up to 99. So the sum is equal to 5 times 99. So 5 times 99 is 495. And we would have gotten the same thing if we listed all 10 terms out and added them up, or if we use this formula directly, the sum of the first 10 terms is the first term, 9, plus the last term, 90, plus the number of terms, 10, divided by 2. So again, that gives us 99 times 5, which is 495. Okay, go ahead and try that out on example B. Press pause and try it out on your own. When you're ready to check your answer, press play. So if I list out a few terms of this series, I would first plug in 1 and get 7 times 1 plus 2, so that is 9. And then plug in 2, I get 14 plus 2 is 16. Plug in 3, I get 21 plus 2 is 23, and so on and so on. And then the second to the last term, when I plug in 11, would be 77 plus 2 is 79. And then plug in 12. 7 times 12 is 84, plus 2 is 86. So we can see in this sequence, this is definitely an arithmetic sequence. It's going up by 7, up by 7, up by 7 consistently. So our common difference is 7. The sum of the first 12 terms, using the formula we found earlier, is the first term, 9, plus the last term, 86, plus the number of terms. If I count from 1 to 12, that's 12 terms divided by 2. So that the 12 divided by 2 tells me how many pairs that would be, and so that is 95 times 6. 95 times 6 is 570. So the sum of all of these terms, going from 9 all the way up to 86, would equal 570. Okay, there's one more for you to try here. Go ahead and press pause, try it out, and then check back in to see your answer. So in this series, we start off by plugging in 1 again. That gives us negative 4 plus 6 is 2. And then plug in 2. Negative 8 plus 6 is negative 2. So you can think of it as plus negative 2 or just minus 2. It works the same either way. When we plug in 3, we get negative 12 plus 6, which is adding negative 6, and so on. The second to the last term, when I put in 19, negative 4 times 19 plus 6 is negative 70. And then the last term, when I plug in 20, negative 4 times 20 plus 6 is negative 74. So we see for all of these terms, from one term to the next is a difference of 4. So we add 4. We actually are subtracting 4. We're going down by 4. So we're adding negative 4, add negative 4, add negative 4, and so on all the way across. So our common difference is negative 4. The sum of the 20 terms that we have here is the first term, 2, plus the last term, negative 74, times the number of terms, which is 20. I go from 1 to 20, so that's 20 terms, divided by 2 to get the number of pairs. And so that is negative 72 times 10 is negative 720. So the sum of this entire series is negative 720. And that completes our lesson on arithmetic sequences and series. If you need to go back and watch any of these parts again in order to complete some of the exercises in the book, you can always come back to this whenever you need to. Good luck.